What do you think is most important? If I apply a force for a long time on an object, will it gain a lot of energy? Always? If you think of that block, it seemed like the longer we applied that force, the more it would accelerate, the more velocity it would gain, the more energy it would have, the greater the damage it causes when it hits me. Right, so it seems like if we apply a force for a long time, we get more energy. But the problem with that is, what if we've got a situation like this? I've got the same block, same surface, but the force is now applied downwards. Right, and the block does not move through the surface, so it means there must be a normal force of the same magnitude that is opposing the motion of the block. Now, if I stand over there, I can wait and wait and wait and wait, and that applied force can be applied for a long, long, long time. It's not going to change anything in this picture in any meaningful way. So it's not enough to say, okay, well, if a force just acts, the longer a force acts on an object, the more energy the object will have. What actually is important is that the object has to move. So the direction of the force is important. And if this force is applied in such a way that this block actually accelerates, so if I completely change the direction of the force so that the block moves by a certain distance, delta x, we can say the larger the distance over which this block moves means the more it will accelerate, the more velocity it will gain, which means the more energy it will have. So what's actually important here is not that the length of time for which a force is applied, but actually the magnitude of a force in the direction of motion multiplied by how far this object is moving. And this is equals to, or should be roughly equal to, give an idea of the energy transferred to the block. And this quantity we just call the work that is done by the force F. So we've looked at two cases. Here we've got a force, but we've got no displacement, so no transfer of energy. So we say no work is being done. Here we've got a force in the direction of motion. So we've got a force, we've got a non-zero displacement, and we've got lots of energy transferred. If we've got a force, say, acting in a direction, let's say we've got a force like this, that's the applied force. We've got the weight of this block, and there is some sort of normal force acting on the block, and this block is displaced again a distance delta x. We can split this force up into two components. We can say that there's a component of this force that acts parallel to the normal force, so it's not to scale, it would be more like that. And there would be a component that is parallel to the direction of motion. And this component, because there's no displacement in the y direction, so this component plus the normal force is just enough to counter the weight of this object. You can think of this component of the force as almost being wasted. It's not contributing anything meaningful to this block. It's not changing its state in any real way for this particular case. However, this component of the force, the x component, the one that's in the direction of motion, that's the component that is actually being utilized to accelerate this block. Because we know from Newton's law, this block will, if the forces along the vertical cancel, this block will accelerate in the x direction. So the larger its acceleration in the x direction, the more energy it gains. The only thing accelerating it in the x direction is that x component of the force. So it's actually, if I apply a force to an object, I can do work with that force, but it's only the component of the force that's actually in the direction of motion that will be utilized effectively. The rest, the other component, is wasted in a sense.